पवित्रवतु।
Good afternoon. Today I am going to discuss chemistry of group 13 elements. Now why I have selected this topic? There are two reasons for it. First is group 13 elements form an interesting type of compounds called as electron deficient compounds, and they exhibit what is known as inert pair effect. Now before we start with the chemistry of any elements, we should first know the position of elements in the periodic table. Now it is not necessary to draw the entire long form of periodic table over here, but we will draw what is all. I have drawn what is known as a block diagram of periodic table. Now you know that on the basis of electronic configuration, elements are classified into 4 different types: S block, P block, D block and F block elements. Okay, so here we have S block elements, here we have P block elements, here we have D block elements, then we have F block elements. So what is the position of these group 13 elements in the periodic table? They belong to P block. This is group 13. Now you know that now we number the groups from 1 to 18. Earlier they were numbered or they were subdivided into group A and group B. But now we number them from 1 to 18. Okay, so these are our group 13 elements. Now let us see which are the group 13 elements. So group 13 elements are boron, aluminium, gallium, indium and thallium. Now once you know the position of element in the periodic table, you should know the electronic configuration of the element. Why? Because all the properties are related to electronic configuration, and electronic configuration decides its position in the periodic table. So when you see the electronic configuration of these elements, what do you find? All these elements they have, you can say they have a general valence electronic configuration of NS2 NP1. Now what are S block elements? In S block elements, the differentiating electron or the characteristic electron enters the S subshell. In P block elements, the characteristic electron enters the P subshell. In D block elements, the characteristic electron enters N minus D subshell, whereas in F block elements, it enters N minus 2 F subshell. Okay. So all our group 13 elements have general valence electronic configuration of NS2 NP1. So they have their characteristic electron in the P subshell, and therefore they are called as P block elements. Okay. Now as they have same general valence electronic configuration, they are expected to have same properties, but still they have some difference in their properties. So what is the reason for it? Now the first reason is position of these elements in the periodic table and electronic configuration of inner shells. Okay, so when you consider these elements, boron, aluminium, then boron and aluminium, which are first two members of group 13 elements, they immediately follow the S block elements. Whereas when you consider gallium, indium and thallium, then they follow d block elements or they have electrons in their d subshell. Whereas when you consider thallium, it has d and then 4f subshell. So this position in the periodic table is important. At the same time, when you consider boron and aluminium, in the inner shell, they have inert gas configuration of either 2 or 8 electrons. Okay. Whereas when you consider gallium, indium and thallium, then in their inner shell, they have electronic pseudo-inert gas configuration. They have 18 electrons. This is called as pseudo-inert gas configuration. So because of these two reasons, their position in the periodic table is different. The electronic configuration of their inner shells are different, and as a result, these group 13 elements can be divided into, you can say, two types. One consisting of boron and aluminium, and then gallium, indium and thallium on the other side. Now what is the distinct difference in their properties? Now when you consider S block elements, in S block elements you have what? All metals. What you have? You have alkali metals, then you have alkaline earth metals. When you consider D block elements, you have all transition metals. But when you consider P block elements, there is a variation in the metallic property in the same group as you go down the group. Okay, in all other blocks you have distinctly metals, all metals. There is no variation in the metallic property as you go down the group. And group 13 element, they mark the beginning of this train of change in metallic character. And therefore, group 13 elements are important because they mark the beginning of this train. Okay. Now let us see what are electron deficient compounds. Now what are electron deficient compounds? We can define them as the compounds in which the valence electrons which are available for bonding are less than the minimum number of electrons required for covalent bonding. Now all these group 13 elements, they form electron deficient compounds. Now boron forms several boron hydrides. Now what are boron hydrides? Compound of boron and hydrogen. So boron forms a number of boron hydrides which are electron deficient compounds. Now these boron hydrides are called as boranes by analogy with alkanes. Now these boranes can be divided into two classes. One class is having general formula BnHn plus 4. The example is diborane, that is B2H6, and other class which have general formula BnHn plus 6, that is B4H10. They are called as hydroboranes. Now when you consider these two types of boranes, or out of these two types of boranes, the class 1 type of boranes, they are more stable and they are well studied as compared to class 2 type of boranes. Then aluminium aluminium, gallium, indium and thallium, they form a number of alkyl compounds which are electron deficient compounds. Okay, and aluminium and gallium, they form a number of halides of the type M2H6 which are also electron deficient compounds. That means when you consider the group 13 elements, all the group 13 elements, they form electron deficient compounds. But when we are going to discuss electron deficient compounds, we are going to take example of simplest molecule which is diborane molecule. So with the help of diborane molecule, now let us see what is an electron deficient compound. Now when you consider B2H6 and C2H6, that is ethane, they have got similar formula. Okay. Now when you consider this ethane, how many atoms are there in the molecule? There are 8 atoms in the molecule. So if these 8 atoms are to be held together by simple covalent bonds, because we know that in ethane molecule you have simple covalent bonds, then you require minimum 7 covalent bonds. Okay, so we can draw this. So for holding these 8 atoms together, we require 7 bonds. Now for each covalent bond, you require 2 electrons. So for these 7 covalent bonds, how many electrons are required? You require 14 electrons. Okay. So in ethane molecule, these 14 electrons are available. So it is not an electron deficient compound. Now how we have got here, I have shown the number of electrons, but we can actually count the electrons. Now in carbon atom, how many valence electrons are there? There are 4 valence electrons. Now I am considering only valence electrons because for bonding only valence electrons are involved. So in C2H6, for each carbon atom, there are 4 valence electrons. How many carbon atoms are there? 2. There are 2 carbon atoms, so that accounts for 8 electrons. Okay. Then there are 6 hydrogen atoms, so they account for 6 electrons. So you have 8 plus 6, that is 18 electrons, that is 14 electrons. So in ethane molecules, you have the sufficient number of electrons available for the covalent bonding. So it is not an electron deficient compound. Now let us consider example of this diborane. So in diborane, for each boron atom, how many valence electrons are there? There are 3 valence electrons. So 2 boron atoms, they contribute, how many? They contribute 6 electrons. Then there are 6 hydrogen atoms which contribute 6 electrons. So how many total electrons are there? There are total 12 electrons. So that means you actually require 14 electrons, but there are only 12 electrons available for bonding, and hence diborane is an electron deficient molecule. Now there are no minimum number of electrons are not available for bonding. Then what is the type of bonding in diborane or what is the type of bonding in electron deficient compound is very interesting to know. So let us see now the structure of diborane molecule and the bonding in diborane molecule. It is not drawn up to the scale, it is just a schematic representation. Okay. Now, X-ray diffraction studies, they show or they give the following structure, the above structure which I have drawn on the board for diborane molecule. So, in diborane molecule, there are 4 terminal hydrogen atoms which are bonded to 2 boron atoms. Now, these 2 boron atoms and 4 hydrogen atoms, they are coplanar, and remaining 2 hydrogen atoms, they are called as or they are involved in the formation of BHD bridge, and hence these 2 hydrogen atoms, they are called as bridge hydrogen atoms, and these bridge hydrogen atoms, they are perpendicular to the plane of these 2 boron atoms and 4 terminal hydrogen atoms, and this structure is further confirmed by specific heat measurement and by the study of Raman spectra. Then again, by the manner in which this diborane undergoes methylation or substitution reaction, this structure can be confirmed. Now what happens is, if you substitute C2H6 for methylation, then all the 6 hydrogen atoms are substituted by methyl group. So what does that indicate? All the hydrogen atoms are of same type and they can be easily substituted. But when you subject B2H6 for methylation, it first gives you B2H2 CH3 4. That means out of 6 hydrogen atoms, first only 4 hydrogen atoms are substituted, and therefore you get B2H2 CH3 4. Now if further you force methylation on this, if you further force it for methylation, then what happens is molecule breaks and you get 2 BCH3 units. Okay, 2 BCH3 thrice units. What does that indicate? The 4 hydrogen atoms are such that they can be easily substituted and their substitution does not lead to breakage of the molecule, whereas the remaining 2 hydrogen atoms are such that if we try to substitute them, then that leads to breakage of the molecule. So in diborane molecule, there are 2 types of hydrogen atoms, 4 terminal hydrogen atoms and 2 bridge hydrogen atoms. So now let us see what is the type of bonding. We have seen the structure, now let us see the type of bonding. So what is the valence electronic configuration? It is 2s2 2p1. Okay, so we will show it like this. Now in the excited state, what is happening is one of these electrons is excited to higher p energy level, and then we have sp3 hybridization. Okay, so in B2H6 molecule, boron atom undergoes sp3 hybridization. Now this arrangement of 4 hydrogen atoms is approximately tetrahedral. Okay, so around each boron atom there are 4 sp3 hybrid orbitals. Now out of these 4 sp3 hybrid orbitals, 3 orbitals are filled with a single electron and 1 orbital is vacant. Okay, so I will shape these orbitals because they are filled with a single electron and 1 orbital is vacant, so I have kept it vacant. I will put the lines in that. Similarly, on the other side also you have another boron atom which also has 3 filled sp3 hybrid orbitals and 1 vacant sp3 hybrid orbital. Now there are 2 types of hydrogen atoms. 4 are terminal hydrogen atoms. So these hydrogen atoms, they also have 1 electron in their 1s subshell. So that 1s subshell of one of the hydrogen atoms overlaps with 1 sp3 filled hybrid orbital of boron. Then second hydrogen atom overlaps with the second filled sp3 hybrid orbital of boron. Now this boron is left with 2 sp3 hybrid orbitals. One is filled with electron, another one is vacant. Now on this side also, this boron also has 3 sp3 hybrid orbitals which have a single electron and 4th orbital which is vacant. So these 2 orbitals overlap with 1s orbital of hydrogen. So there are these 4 terminal hydrogen atoms, and then this boron also has 1 vacant sp3 hybrid orbital and 1 filled sp3 hybrid orbital. So when you consider the bonding in B2H6 molecule, what you find that these 4 terminal hydrogen atoms, they are bonded to the boron atom by normal covalent bonds. Then where does that electron deficiency comes into picture? That comes into picture for this BHB bridge. Okay. So here now what is happening is, on one boron there is 1 filled sp3 hybrid orbital. Then on another boron you have 1 vacant sp3 hybrid orbital. So 1 filled sp3 hybrid orbital of 1 boron and 1 vacant sp3 hybrid orbital of another boron overlaps with 1s orbital of hydrogen, which you can say is a bridge hydrogen. Similarly, here also 1 vacant. Now this atom has 1 vacant sp3 hybrid orbital. So this vacant sp3 hybrid orbital of first boron and the filled sp3 hybrid orbital of another boron, they overlap with 1s orbital of hydrogen, and you get what is known as a 3-center 2-electron bond. So see here, for 4-terminal hydrogen atoms, the bond is a normal covalent bond. But for BH bridge, it is a 3-center 2-electron bond. And why it is so? It is because of the electron deficiency in the molecule. So we can just represent it pictorially like this, and then it can be shown like this. So because this 3-center 2-electron bond has got a banana type of shape because of the overlapping of these orbitals for BH bond, and hence this bond is called as a banana bond. Okay, so in B2H6 molecule, you have 4-terminal hydrogen atoms which are bonded to 2 boron atoms by normal covalent bonds, whereas the remaining 2 hydrogen atoms, they are bonded in such a way that it is a 3-center 2-electron bond. And this type of bonding is because of the electron deficiency in the molecule, and because of the shape of this bond, it is called as a banana bond. Okay, now let us see what is inert pair effect. Now before we see the inert pair effect, or in fact we can see inert pair effect, or we can discuss inert pair effect while discussing the oxidation states of these elements. Now p block elements exhibit 2 major oxidation states. One is called as group oxidation state, and another oxidation state which is less by 2 units as compared to the group oxidation state. Now what is group oxidation state? It depends on the number of electrons in the valence shell. Now for group 13 elements, the number of electrons in the valence shell is 3. So the group oxidation state exhibited by these elements is +3, and the second oxidation state which is less by 2 units. Now in fact this is true for even group 14, group 15, group 16 elements. All these p block elements exhibit these 2 major oxidation states. So now when you consider our group 13 elements, boron and aluminium, they consistently show +3 oxidation state. Now how this +3 oxidation state can be achieved? Now this oxidation state can be achieved either by the loss of 3 electrons, or one of these s electrons is promoted to 2p shell, and then these 3 electrons immediately form bonds with the other atoms. Now when you consider boron atom, boron is the first member of group 13 element. So it has got very small atomic size and it has got very high ionization energy. So it is very difficult for boron atom to lose all the 3 electrons and to get B3 plus ion. So this ionic compounds of boron, in which boron is in +3 oxidation state, is very difficult to get. So boron attains this +3 oxidation state by covalence. Now when you come to aluminium, aluminium also exhibits distinctly +3 oxidation state, but aluminium 3 plus compounds can be ionic. Why they can be ionic? Because if Al3 plus ion, it has also small atomic size, it gets hydrated extensively, and when it gets hydrated, lot of hydration energy is liberated and that stabilizes Al3 plus ion. Now when you consider other members of the group, cadmium and indium, they do show some compounds which are in +1 oxidation state. But that +1 oxidation state is immediately converted, or those compounds are immediately converted to compounds in which it is in +3 oxidation state. But when you consider the last member of the group, that is thallium, then it exists exclusively in +1 oxidation state. So what does that indicate? That means in group 13 elements, as you go down in a group, the stability of higher oxidation state decreases and that of lower oxidation state increases. And this is because what is called as inert pair effect. And this effect is exhibited by all the p block elements. That means in all the p block elements, as you go down the group, the stability of higher oxidation state, it decreases and that of lower oxidation state increases. Now why this is happening? Now see, for boron, it has valence configuration 2s2 to p1. Okay, so it has 1 electron in p shell and a pair of electrons in ns shell. Now if all these 3 electrons are lost, or if they are used in bond formation, then you get +3 oxidation state. But many a times only this p electron can take part in bonding, whereas that pair of ns electrons will remain intact. And this is but obvious because p electrons are away from the nucleus as compared to s electrons. So it is very easy to remove this p electron. So sometimes only this p electron takes part in bonding, or it is not, and pair of ns electrons does not take part in bonding. Then you will get +1 oxidation state. If all these 3 electrons take part in bonding, then the oxidation state will be +3. Okay, but if that pair of s electrons remains intact, or if it remains inert, and only p electron is involved in bonding, then you get +1 oxidation state. Now what is happening is, as you are going down the group, for example for this group 13 elements, then this pair of ns electron becomes reluctant to take part in bonding, or it becomes inert towards bonding, and this is called as inert pair effect. So what is inert pair effect? It is the reluctance or the inertness of the pair of ns electrons in taking part in bonding. So when this pair of ns electron does not take part in bonding, what happens? You will get +1 oxidation state, okay, and not +3. So this inert pair effect becomes more pronounced in the last member of p block elements. Because just now we have seen the oxidation states exhibited by all these elements. So all these elements, they show +3 oxidation state, but the last member of the group, it distinctly shows only +1 oxidation state. So what is the reason for it, or what is the reason for the inert pair effect? Now we can give two types of explanations for this inert pair effect. Okay. Now first explanation, you can say it is a qualitative explanation. Now in the beginning I have told you that for boron and aluminium they follow S block elements. Before boron and aluminium you have S block elements. Okay. Whereas for gallium and indium they have electrons in the d subshell, and for thallium it follows F block elements. So before this thallium we have 14 lanthanides or 14 F block elements. So by the time you come to thallium, the nuclear charge has increased tremendously, and as a result of this increased nuclear charge, that pair of S electrons is held very tightly by the nucleus and it is not available for bonding. So this is a qualitative explanation for the inert pair effect. Now what is another explanation? Now let us see here, this one electron can be promoted to one of the p subshells, and then you have these electrons here. Now they can immediately form bonds with other atoms, and during this energy is released, which is the bonding energy, and these bonding energies, if they are higher than, now what is happening, this pair of electrons is getting unpaired. So lot of energy is required for this electron to get unpaired, but as these electrons then form bonds with other atoms, some energy is released, and that compensates for this high bonding energy. Now for p block elements or even for this group 13 elements, as you go down the group, these bonding energy values they decrease. So what happens, by the time you come to thallium, that bonding energy or that energy that is liberated when these 3 electrons form bonds with 3 atoms, it is very less. So it does not compensate for the high amount of energy that is required to unpair this electron. And as a result, as you go down, or specifically when you come to the last heavier element or p block or for group 13 element, that pair of electron becomes inert or reluctant to take part in bonding, and only one p electron can be removed or it can be involved in bond formation, and as a result, as you go down the group, only lower oxidation state is stable, and for other members of the group the higher oxidation state is more stable. Okay, so thank you.